Hello everyone, this is Professor Roman. Let's continue the field theory lectures. Let us now turn to the most general case, and that is an arbitrary algebraic extension of the domain. Now, since this algebraic extension may be infinite, you might assume we're going to need a little bit more powerful tools for this case, and you would be right. That tool is Zorn's lemma. The simple case, together with Zorn's lemma, is just what we need to prove that any embedding sigma from a field F to an algebraically closed field L can be extended to any algebraic extension of F. So, suppose that Fe is algebraic and L is algebraically closed. Any embedding sigma from F to L can be extended to an embedding sigma bar from E to L. Moreover, and we've seen this before, if an element alpha in E has this minimal polynomial, and if beta in L is a root of the image of that minimal polynomial, then we can choose sigma bar to send alpha to beta. For the proof, let script E be the set of all extensions, tau, embeddings of K into L. This is an extension of sigma to any intermediate field K for which alpha is in K and tau sends alpha to beta. Those are the requirements we want to cover part 2 here of the theorem. First, we have to make sure E is not empty. But theorem 211 implies that sigma, that's the simple case, implies that sigma has an extension, and I used the notation sigma alpha beta, mapping F with alpha joined, so that's a simple algebraic extension of F, into L. And this map sends alpha to beta. That belongs to the family E, so we know at least ED is non-empty. Now the set E is partially ordered by extension, so this embedding is less than or equal to this embedding if this one, tau prime, is an extension of tau. So K prime is an extension of K. To apply Zorn's lemma, we need to look at an arbitrary chain in E and find an upper bound. Well, we can take the union of the domains and map that union into L by tau, and tau is defined by specifying that when we restrict tau to one of the domains, k sub I, we get tau sub I. I said it's well defined, and I'm going to leave it for you to justify that. It has to do quite strongly with the fact that this is a chain under extension. In any case, this map is an upper bound for the chain. It also belongs to E, so it's an upper bound in E for the chain. And so Zorn's lemma implies the existence of a maximal extension. We'd like to show that K is equal to E, and that will be our extension sigma bar. But if K is a proper subset of E, then there's an element gamma in E that's not in K. It's algebraic over the base field, so we can do a further extension. And that contradicts the maximality of tau. So K is in fact equal to E, and tau is an embedding of E into, that should be L. and that extends sigma. As a corollary to this result, we have a couple of very important results. First is the essential uniqueness of algebraic closures. By essential uniqueness, I mean, of course, uniqueness up to isomorphism. We can be a little more general, in fact. It's true that if two fields, F and E, are isomorphic, then any algebraic closure of F will be isomorphic to any algebraic closure of E. If the base fields are algebraic, their algebraic closures are isomorphic, their algebraic closures are isomorphic. And here's the corollary. Look at this figure. Sigma is an isomorphism between the fields F and E. Now we do know from the previous theorem that we can extend sigma to F bar, because that's an algebraic extension of F. What we get from the previous theorem is an embedding of F bar into E bar. So I've drawn the image here of sigma bar down here. However, the full extension is algebraic, so the upper step is algebraic. But since F bar is algebraically closed, so is its image under sigma bar. However, an algebraically closed field doesn't have any proper algebraic extensions. So E bar is equal to sigma bar F bar. And therefore sigma bar is an isomorphism from F bar to E bar. That's the extension of sigma. So this is a direct consequence of the theorem we just proved. So is the next result concerning splitting fields. They are also essentially unique. Just for completeness, I've included the result we talked about quite some time ago about existence of splitting fields. So let P be a non-empty family of polynomials over a field F. Any algebraic closure, F bar of F, contains a unique splitting field for P. And that was theorem 1.63. Part 2 here says that if we have two algebraic closures of F, L and M, inside there are unique splitting fields, S1 and S2, then S1 and S2 are isomorphic. Well, we do know from the result we just proved that there is an isomorphism lambda between the two algebraic closures of F. If we restrict that map, lambda, I'll call it lambda 1, restrict it to the splitting field S1, this is now an embedding of S1 into M. If R sub k is the family of roots of the polynomials in P that are contained in Sk, and k could be 1 or 2, then the splitting field Sk is F with Rk adjoint. But lambda 1 of R1 is the set of roots of P in S1, in S2. If we take R1, this is the set of roots for the family P, the set of roots that belong to S1 or L. It's the same thing. We map that by this restriction restricted map, where to go here, there it is, S1 into M, we get a set of roots for the family of polynomials now that's sitting in S2. So lambda 1 of R1 is contained in R2. But for each polynomial in the family, this embedding, lambda 1, maps the root multiset for the polynomial in S1 onto the root multiset for the same polynomial in S2. It maps roots to roots and preserves multiplicity. So lambda 1 actually maps the root set, the root multiset if you want, the root set R1 onto the root set R2. So not only does it map roots to roots, but it maps roots to all of the roots. And so lambda 1 of S1, S1 is F with the root set adjoined, and since lambda 1 fixes F pointwise, this is F with lambda 1 R1 adjoined, or in other words, F with the other root set adjoined, the one that lies in M, and so that's S2. So we have an isomorphism. This was an embedding, but this is the range. So this is now surjective also. Okay, so there is one more matter that we need to discuss concerning the general algebraic case. We've seen that extensions are possible, but we haven't discussed the issue of separable degree. So let's do that now. The class of algebraic extensions has separable degree. So this is what we need to prove. We have to show that if Fe is algebraic, and if we have an embedding sigma from F to L, so let's look at the figure here. Sigma maps F into L, so here's the image, sigma F. And tau also is an embedding of F into L prime. L and L prime are algebraically closed, as always. That the cardinalities of the set of extensions of sigma to E and the extensions of tau to E are the same cardinalities. That's what it means to have a separable degree. Well, let's note first that L and L prime, they're algebraically closed, but we can replace them if by the algebraic closure of sigma F and tau F. And the reason is this. In this tower, sigma F, sigma bar E, so sigma bar is an extension of sigma L, this tower has the lower step is algebraic because Fe is algebraic, and so sigma F, sigma bar E is also algebraic. And so sigma bar E is contained in the unique algebraic closure, which I'm calling A, of sigma F inside L. There's a unique algebraic closure of sigma F, and it's the same as the algebraic closure of sigma bar E that's contained in L. I called that A. Since this extension is algebraic, sigma bar E is contained in A. So sigma bar, in fact, maps E into A. Put it more generally, any extension of sigma to E is going to map E into A. So we have more, so to speak, than we need here. The elements of L that are not in A are irrelevant to this discussion of extending embeddings. So we can reduce the codomain from L to A. A is algebraically closed, so we haven't lost anything. Well, rather than bother to introduce A and A prime over here, we can just assume that L is an algebraic closure of sigma f. So not only is L algebraically closed, but it's an algebraic extension of sigma f. And L prime is similarly an algebraic closure of tau f. And the reason we want to do that is so we can apply the previous result, 2 results ago, on the extension of an isomorphism of fields to their algebraic closures. So what we want to do to show that these cardinalities are the same is to do it in 2 steps, show that one cardinality is less than or equal to the other, and then a symmetric argument will give us the reverse inequality. Well, if you look down here at the bottom, and you start here and you apply sigma inverse, it's an isomorphism between f and sigma f, apply sigma inverse, then apply the isomorphism tau, you get an isomorphism of this field and this field. And that can be extended, so that would be sigma inverse followed by tau. That can be extended to an isomorphism between the algebraic closures. So lambda here is an isomorphism from L to L prime. Oh, I'm sorry. Lambda is an isomorphism from L to L prime. It's the extension of this isomorphism at the bottom here. Okay. So so now we can define a map using lambda here. We can define a map that sends this set of extensions to this set of extensions, and it is followed by lambda. So we take an extension here, sigma bar of sigma, and we follow it by lambda. And we get now a map from E into L prime. Okay. That's an embedding. So here it is. I've used this notation, lambda upper arrow. I've used it in past courses. It tells us to apply lambda after the map rather than before the map, which would be an arrow pointing the other way. This notation is not very common, but it helps me remember what I'm doing, so I kind of like it. So the arrow pointing to the left means put lambda after the element of the domain. This is an embedding because lambda is an isomorphism. So if we apply lambda back arrow to tau and mu in the domain, if those are equal, that means lambda tau equals lambda mu, which means tau equals mu. Just apply lambda inverse. So I have an injection from here to here, which means this cardinality is less than or equal to this cardinality. Reverse the roles of tau and sigma and get the reverse inequality, and therefore we have this equality. In case you're finding this a little hard to follow, I don't blame you. I think I did when I saw this originally for the first time when I was a student many, many years ago. So don't be discouraged. This is not easy material by any means, so we may have to go through it a few times before it begins to sink in. Let's examine now the relationship between separable degree and separability. The term separable degree wasn't chosen by accident to have the word separable in it. We have seen, for the case of finite simple extensions, that the separable degree is given by this relationship. And this tells us immediately that the extension is degree-wise separable if and only if alpha is separable. So the separable degree is equal to the degree if and only if alpha is separable. That's quite clear because p is greater than or equal to 2. Now, we want to generalize this. So suppose first that Fe is a finite extension. That's equivalent to saying E is finitely generated over F by algebraic elements. So E is F with S adjoined, where S is a finite set of algebraic elements. If this finite extension, so this is an arbitrary finite extension, if it's degree-wise separable, and if we take an element beta in F with S adjoined, and look at this tower, remember we proved that degree-wise separable extensions have the tower property. So if F to Fs, the full extension here, is degree-wise separable, so is in particular the lower step. But that tells us then that the generator is separable, so beta is separable. But beta was an arbitrary element of F with S adjoined. Therefore, the extension is separable. What that means is that every element in here is separable over F. Okay. I should always add a little sloppy here. I should say over F. I think I've said this before, but all these little peccadillos you see will be corrected before I post the book on my website. So what we now know is that FFS degree-wise separable, this is for finite extension FFS, degree-wise separable implies that the extension is separable, meaning every element in Fs is separable over F, so in particular the generating set is separable over F. For the converse, if we have a finite extension and say S is the set alpha 1 through alpha n, and it's separable over F, so we're starting with this, then we can decompose to a tower of simple extensions. Each step is simple, and because each generator is separable over F and therefore over any field containing F, and I'll let you ponder that, it follows from, let me get this back again, from the simple case, that each step is degree-wise separable. And so the tower property tells us that F to Fs is degree-wise separable. So if S is separable over F, this extension is degree-wise separable. So that completes the loop back. And so now we have equivalences here. For a finite extension, Fs is degree-wise separable if and only if it's separable, if and only if it's separably generated. There's still one more step here, We can go one higher in generalization. Suppose that FFS is algebraic. We're not assuming it's finite. Any algebraic extension has this form. If this extension is separable, then of course S is separable again over F. Okay. For the converse, suppose that FFS is separably generated by S. And suppose beta is an element of Fs. Then there is a finite subset, S0 of the generating set, that for which beta lies in Fs0. But now this is finitely separably generated. It's a finite extension that's separably generated, so we can apply what we just learned here, and it tells us that it is separable. So beta is separable over F. And so this is separable, therefore beta is separable over F. Beta was an arbitrary element of F with S adjoined, so this extension is separable. And we can summarize. The following are equivalent for an algebraic field extension, Fe. It's separable, it's separably generated, and if it's finite, it's degree-wise separable. This is a remarkable result. We've done quite a bit of mathematics here. To say that Fe is separably generated is to say that it has a generating set, each element of which has a minimal polynomial with no multiple roots. Jumping from that to the fact that every element of E, not just a generating set, has that property is quite a step. And that's why it took us quite a bit of work to get to it, to show these two are equivalent. So, let's summarize all of our results for the various types of extensions of the domain of an embedding. If we have, so sigma is an embedding of F into an algebraically closed field L. For a simple extension of the domain, simple and finite, I should always say that, we can find an extension, which I've been calling sigma alpha beta, of sigma that maps alpha to beta. All extensions have this form, so we have a real clear picture on what the extensions of sigma look like when we extend the domain by adjoining a single algebraic element. As for the number of extensions, we have this formula. D is the radical exponent. In particular, the separable degree divides the full degree. I shouldn't say full degree. This is the vector space dimension. When we have an algebraic extension of the domain, any embedding of F into L can be extended to an embedding of E into L. And we can specify, as before, we can send alpha, a particular alpha to a particular beta. We have the divisibility here, separable degree divides degree. We have the multiplicativity of separable degree. These two, of course, apply only when the extension is finite. Not the previous A and B were for general algebraic extensions. And finally, we have this little tidbit here that we worked hard to get. on the connection between separable, separably generated, and degree-wise separable. We have one more item of business with respect to separable extensions. The class of separable extensions is strongly distinguished. As for the tower property, if the full extension in this tower FKE is separable, then so is the lower step, and I'll let you ponder that. As for the upper step, for any alpha in the bigger field, but in E but not in K, the minimal polynomial of alpha over K divides the minimal polynomial of alpha over the smaller field F. And so if alpha is separable over F, then it's also separable over K. And so the upper step is separable. Suppose now that the two steps, Fk and Ke, are separable. And let alpha be in E, we want to show it's separable over F. Let C be the set of coefficients of the minimal polynomial of alpha over K. That minimal polynomial is then the same as the minimal polynomial of alpha over F with C adjoined. And so alpha is separable over this field, F with C adjoined. And therefore, each step in this tower is finite and separable. And so the equivalence of separability and degree-wise separability for finite extensions shows that the upper step, the full step here is separable. And so alpha is separable over F. As for closure under lifting, suppose Fe is separable and K is an extension of the lower field F. Since every element of E is separable over F, it's also separable over the larger field K. We went through that argument a minute ago. And so the composite EK, which is also K with E adjoined, is separably generated by E, and therefore is separable. So these two, the tower property and the lifting property, tell us that the class of separable extensions is closed under finite composites. To see that they're closed under the taking of arbitrary composites, suppose that Fe is separable. E sub I here is separable for all members of a family of field extensions. Then any element in alpha in the join of the family is in the join of a finite subfamily, F naught of F. And so closure under finite composites implies closure under arbitrary composites.